Okay, so we're now ready to state and prove the second criterion of integrability. So that will be number 10. So it's going to be stated as follows. F is Darboux integrable on the interval AB. As usual, f is the bounded function on AB. If and only if for every epsilon greater than 0, there exists a delta greater than 0, such that mesh of P less than delta implies that U of P, Fp minus L of Fp is less than epsilon. Right, so again, your function is Darboux integrable on the interval AB. If for any epsilon greater than 0, there exists some critical size of the mesh, if mesh is less than a certain number, then the difference between upper and lower Darboux sum is going to be less than that epsilon that you prescribed. So again, mesh, if you remember, is the maximum length of an interval, of a subinterval in a partition P. And basically then this says that if you continue refining your interval AB, refining your partition of the interval AB, then the difference between overestimation and underestimation can be made as small of the overestimation, underestimation of the area can be made as small as you wish. Okay, so let's try to prove this. The proof in one direction should be actually trivial. If such a partition exists, right, so if epsilon delta, if this epsilon delta definition of integrability holds, if for every epsilon there is a delta such that U of Fp minus L of Fp is less than epsilon, as long as mesh of P is less than delta, then this basically is the first criterion of integrability, right? I can always find the partition with a mesh which is less than delta, right? If I have an interval AB, if I divide its length by a sufficiently large number n, then I can find a partition with mesh which is less than delta. For that partition, automatically the circle difference is less than epsilon. So then there exists a partition of my interval such that U of Fp minus L of Fp is less than epsilon. So then the first criterion of integrability implies that f is integrable. So going in this direction, this follows from the first criterion of integrability. And so we only need to prove this statement going in this direction. Okay, so suppose that f is Darboux integrable on AB, So then I'm guaranteed and this is the first criterion of integrability, that there exists a partition P epsilon of AB such that U of Fp epsilon minus L of Fp epsilon, that this quantity is less than epsilon divided by 2. Okay, so we have that. I'm going to denote by M the number of points. Actually, let's do the number of intervals of subintervals. In P epsilon, and also let B be such that have the same meaning as what it had in our last lecture, be such that because the function is bounded, right? So that's what we have. And further, at this point is going to be mysterious, but let's do this. I'm going to set delta be epsilon divided by 8 MB. All right. So this is what we have. And now let's choose any partition P such that mesh of P is going to be less than delta. And consider the refinement of P given by Q, that is a union of P epsilon and P, right? So Q has all the points of P and all the points of P epsilon in it. All right, so if that is the case, let's see, what can we say about Q? Q is a refinement of P epsilon as well, right? Is also of P epsilon. And so then in particular, because it's a refinement of p epsilon, then what we have is that u, right, remember we talked about that last time, when I do a refinement of a partition, then upper Darboux sum goes down, lower Darboux sum goes up, so the difference between upper and lower goes down. So then u of fq minus L of fq is going to be less or equal than u of f p epsilon minus L of f p epsilon, right? Because that is q is a refinement of p epsilon. Okay, fine. And what do I know about p epsilon? I know that u of f p epsilon minus L of f p epsilon, that this quantity must be less than epsilon over 2, right, by our assumption. So this is less than epsilon over 2. Okay, so that's fine. But this actually is not what I am trying to show, right? I'm trying to show that as long as mesh of P is less than delta, then U of Fp minus L of Fp, that must be less than epsilon, right? But we know the statement about Q. So what we want to show that U of Fp minus L of Fp is less than epsilon, and we have a statement about Q where the difference actually is even smaller, right? It's less than epsilon over 2. Well, what do we know about Q again? So Q is a refinement of P, right? And then so if Q has one more point, then P, then of course U of Fp minus L of Fp is greater than U of Fq minus L of Fq, right? So certainly this number must be greater or equal than this number, right? But I don't know by how much. So if U of Fq minus L of Fq is less than epsilon over 2, each time I remove a point from the partition Q to get to the partition P, I'm actually making this difference larger, right? The one that is circled. And I don't want to make it larger too much because I only want to go from epsilon over 2 to epsilon, right? So what I'm doing now, I'm kind of removing points from Q to get to P, and I don't want to go up in the difference U of Fp minus L of Fp by too much. Okay, so if Q had one more point than P, then by how much can I actually increase my U of Fq minus L of Fq when I go from Q to P? So then, well, yeah, but actually that's something that we proved in the end of the class last time, right? We proved that this should be less, this difference should be less than 4b times the mesh of P, right? So let's actually copy that. right? This is from property 11 that we proved last time. Okay, so then if Q has two more points, what will happen? You sort of repeat the same calculation, and we repeat the same calculation, then you gain 4b times mesh p more, right? Now, what's the difference between Q and P? Q was a union of P epsilon and P. And P epsilon is a fixed partition, which we agreed is going to have m points, right? So then by induction, if I repeat this calculation m times, right, to get from Q to P, I'll have to remove at most m points of the partition P epsilon. And each time I do it, I'm going to gain 4b times times mesh P. So then by induction, since Q has at most m more points than P, we have that same statement, except that I should incorporate m here. Well, but if that is the case, then what did I assume about mesh P? Mesh P was chosen in such a way so that mesh P is less than delta, right? So then this is going to be less than 4mb delta. And how did I define delta, right? So delta was defined in this mysterious way as epsilon over 8mb, but now I hope it's no more mysterious because delta was chosen in such a way that, what is this now? It's 4mb, and delta is epsilon over 8mb, and this is epsilon over 2. Okay? So, what do we have at the end of the day then? We have that if I add this difference to both sides, so then we have that u of fp minus L of fp, this is less than epsilon over 2 plus u of fq minus L of fq. And by assumption, right, because again, q was a refinement of p epsilon, this difference is less than epsilon over 2, so the whole thing is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And that's precisely what we wanted to show. So that means that the second criteria of integrability has been proved and it holds. So if I have a function which is Darboux integrable, or a function is Darboux integrable if and only if for every epsilon I can find some threshold value of the mesh of my partition, such that if mesh has a smaller, if a partition has a mesh which is value smaller than delta, then the corresponding difference between upper and lower Darboux sums is going to be less than my prescribed epsilon. And in the next lecture, I'm going to apply this to the